to handle it. So we'll try to get a TA to come in. So a word about the ME5402 and EE5106. So the focus of this module is essentially on classical robotics. So what is classical robotics? So classical robotics is essentially the study of industrial robotic manipulator. So we're actually looking at it's essentially an integrated approach of kinematics, statics, dynamic, trajectory planning, control strategy, as well as physical hardware. So for today's lecture, I'll briefly run through all these topics. And then for the subsequent lecture, we'll go to them deeply. So I'll be covering the kinematic and statistics, as well as trajectory planning. Dynamic and control strategy will actually be covered in the second half. So the physical hardware, building the robot itself, designing the robot will actually be covered in this lecture. So from here, you can actually see that the focus is essentially on this aspect: the kinematic, static, trajectory planning for the first half, dynamic and control strategy in the second half. So the lecture is on every Monday. We'll start at 6 p.m. So the lecture, I've requested the lecture to be recorded. So the record will start at 6 p.m. So this is why we actually target the lecture to start at 6 p.m. So I will usually try to end the lecture around 8:45, so that all of you can go back, not too late. And then we will try to have a short break around 7 p.m. So the short break will be about 5 to 10 minutes, or 10 to 15 minutes. So this is the venue, LT4, where you are here. So it's going to be a face-to-face lecture. So it's no longer e-learning. So you'll be seeing me and I'll be seeing you. So in the subsequent lecture, I'll bring along a mask, so that if you actually come to me, if you require, I can actually put on the mask. So when I'm at a distance, I will be just talk in this manner. If you cannot hear me, please let me know. So the class info, lecture slides, notes, and tutorial can actually be found on the NUS campus. So I've mentioned earlier, actually this is the first time I've been using Canvas, so I'm actually not very familiar. But yeah, but if I miss out anything, I'll do a mass email. So there'll be no lecture on 23rd January because it's happened to fall on the Chinese New Year holiday. So whether I don't think there's a need for a makeup lecture, but we'll see. If there's a need for a makeup lecture, it will be on the reading week. Sorry, it will be on the recess week. So these are the main texts. So you have the Introduction to Robotics, Mechanics and Control. You also have this Asada book on the robot analysis and control. And then I will announce other reference in the class or via Canvas. So this shouldn't be the luminous. So you can actually find copies of the two books, the Introduction to Robotics and Asaba, on the Ricksport section of the Central Library. So you go to the Central Library, you can actually borrow the books, and then you look at them. So not all materials are from one single books. So it's up. So if you don't want to buy the books, you can actually borrow the book from the Central Library. Okay. So the two books actually cover are kind of different. So the Asada book is actually using something called classical DH notation. And then the Introduction to Robotics using something called modified DH notations. And then for the first half of the course, we are looking at classical DH notation. For the second half of the course, you will actually look at the modified DH notation. They are interchangeable. And then the continuous assessment. So 70% of your grade will actually come from your CA. So there are two CA. There are two parts of the CA. So the part one of the CA will be 35%. So you will have an online quiz. So the online quiz, I'm trying to have it on the Canvas. So you have the whole entire recess week to actually answer the questions. So it's not a sit-down quiz. So you have a whole week at home to do it. So please try to work on the problem on your own so that you can actually understand the type of question to solve the problem. So it's important to know how to solve the problem. The class is actually pretty short, so you only have about 6 weeks. And then minus off the CNY New Year holiday, you have 5. So it's very short, and then you don't really have that much time for your self-exploration. So there will be I will hand out tutorial questions, but I will not be going through them in class. So tutorial question is for you to practice. So there are problems that you can actually try to solve. So the online quiz will be 10%, and then there will be a computing project. So this computing project will be 25%. So it will be due on week 13. So it will be done by a group of at most 3 students. So you're supposed to model a robot manipulator, kinematic analysis, computer simulation of the robot manipulations. So I haven't confirmed on the computing project yet. I will announce the computing project after the CNY holiday. Okay, so the project will actually require you to use MATLAB. So you are required to use MATLAB to do a robotic simulations, a robot manipulator simulation. And then part 2, the remaining 35, the part 2, the remaining they will contribute another 35%. So this will be another mini project. So there are 2 projects, 1 online quiz, and then the final exam will be 30%. So the final exam will only be 1 hour. So there will be 2 questions, and then each question has multiple parts for part 1 and part 2 respectively. So it's a 1 hour exam, open book. So you have to know your topic well. But you don't have to memorize. So you can only bring around your hard copy. So you make sure you make your own notes. Fair? Okay. So this is a grading for the module. Any question? Okay. If no question, we move on to the introduction to robotics. So if we first provide the introduction, so that all of us will actually be on the same page. So naturally, we first define what is actually considered as a robot. Okay, so what is robotics? So actually robotics have been around the word robotic have actually been around for a long time. So it was introduced to a public on a show, on a play called R.U.R. So it published in 1920. So the robot itself actually means forced labor. So this is how so there's a play, there's a movie, and so on. If you actually refer to dictionary.com on the definition of a robot, you will see that the robot will actually define as a machine that resembles a human and does mechanical routine tasks on command. A robot is also defined as any machine or mechanical device that operates automatically with human-like skills. So this is the definition of this is kind of like a layman definitions. So what happened now is we have for the okay. So what happened now is in this course itself we have a lot more other definition of robots. So this is an example. This is also, so if you actually look at this autonomous figure, so it's considered a robot, but it's definitely not human-like. It's not resemble a human. So what happened here is we definitely need a more professional definition of the word robotics. So this is what we are going to go through in the topics of introduction to robotics. I'll be going through the history and applications, the mechanics, the design, the trajectory generation, control, as well as the programming. So a bit about the history. So when we actually look at the development of robotics, it's actually closely tied with artificial intelligence. So in the middle of the 20th century, the research there's actually there's a lot of interest in artificial intelligence. So when we actually talk about artificial intelligence, we're actually looking at the connection between the human intelligence and machines. So the first robot, apart from which is actually different from this robot, was actually invented in 1948. So this is the first robot that actually mimicked lifelike behavior using simple electronics. So 1954, we have the first digitally operated and programmable robot. And then 1956 we have the world's first robot company. And then only to 1961, then we have the first industrial robot that went online onto a GM automobile factory in USA. So the Joseph here is actually referred to as the fathers of the robotics. So it's credited for the birth of the industrial robotic industry. So what happened here is when you actually see this development, the development of the first robot is eventually due to the advances in the mechanics, control, computer, and electronics. So it's very much similar to what happened here. What happened in today's, is still the advances in mechanics, control, computer especially, that's actually driving the field of robotics. So the definition of the robotics will be the science and technologies of robots. So in 1960, we have the numeric control machines for precise manufacturing. So these CNC machines are not exactly a robot. And then we also have teleoperator for remote radioactive material handling. In the 1970s, we have the industrial robot become an essential component for the automations of flexible manufacturing systems. In 1980s, the Professor Kanade actually developed the world's first direct drive robotic arm in 1981. So Professor Kanade is very famous in computer visions. So computer visions and robotics become an important element. So in 1980s, we see the definition of robotics to be defined as a science which study the intelligent connection between the perception and actions. So we move on. In 1990s, we have the field robotics to address the human safety, and then we also have the human augmentations. We also have the service robot. So during this time, the Asimo, which is actually now retired, so it's very popular, and then it actually demonstrates how a robot can actually balance itself on a seesaw. So it's a humanoid robot and designed and built by Honda. Okay. So from 2000 and beyond, we are now actually focusing on human-centered and lifelike robot. So if you are interested in the history of robotics, you can actually refer to this article. So what really matters to us is these two aspects, these two definitions. So from an engineering point of view, robotics is the engineering science and technology of robots and their design, manufacture, application, and structural dispositions. So with this word, you can actually see that a robot will require power supplies, an actuator, a mechanisms, a sensors, as well as an embedded controller, and then this will actually interact with the human user. So another similar definitions that emphasize a lot more on the human interactions will be to define robotics as a science, as a study of the system science that involve perception, cognition, and actions. So this definition is a lot more geared toward computer science. And this definition is probably a bit more closer to what we are doing here. So a robot, so for example, in this case, Asimo, you will actually require a power supply. There's no wire that's actually connected to a master computer. So you need an embedded controller. And then for its movement and so on, to self-balance, you actually require sensors. And then to move, of course, you will actually require an actuator. The whole structure itself is a mechanism. And this, as you know, is actually interact with the external world, with the human user in the external world. So this is the definitions that we are using for this course. The engineering science and technologies of robots and their design, manufacture, application, and structural depositions. There are many applications for manufacture in robotics. So it's used in assembly line. So the robot have been used in assembly line for a long time now. Material handling systems. So this is pretty straightforward when you have the robot that actually move around transporting material and so on. And then for constructions, so for construction, for example, in this case, you have a robot that actually place a steel reinforcement bar, and then, in this case, this robot is actually distributing the cement, the concrete, the cement. This is to move the steel installing bar. This is very much like a crane. So there's also application in farming. You have to pick up the food and then to handle an animal. And then, in fact, farming is an up and coming area for robotics. So this is in 2018. So it's actually talk about the use of robot for in farm. And then, so the robot that's actually featured here is essentially still a rigid. You still have a rigid arm. It's still a rigid something similar to an industrial robot. But increasingly, when we actually want to handle the fruit and all those things, we're actually using something called a soft robot. So for this course itself, we're actually focusing on rigid systems. And then, so we're not going to a rigid system, meaning that the system of particle will not change shapes, will not deform. So, but increasingly, soft robots can actually be used in picking of fruit and so on. So soft robot meaning that it's no longer the robot is no longer can be the shape of the end effector can actually be deformed. So there are other applications, military service and other hazardous related works you will see application in robotics. And then underwater, oil and gas. So you have this ROV, which is referred to as remotely operated underwater vehicle. So this remotely underwater vehicle, there's actually a cable. So this cable is actually connected to the main, to the ship on shore, ship on the sea, on the water. And then they will actually, so it's actually controlled by the ship on top. So when we talk about ROV, so the ROV is actually very much different from ROC. So ROC is, the RCV, remote control vehicle. So remote control vehicle can be on land or can be on air. So this ROV is stand for remotely operated underwater vehicle. So of course, there's a lot on the service robot. So you have a robot street cleaner, a robot usher, and then security guard as well. So robot can also been used for in entertainment. So when you actually look at the use of robot in entertainment, it's actually very different from what we have earlier. So it's no longer used to work to assist a human in accomplish a task, but it's actually now being used to entertain the user. Okay, so in educations, so this is a Lego robot, and then you have a small cute robot that actually interact with kids, and then so this can serve as an educational medium. So aiding the handicraft, the handicapped as well as the elderly. So you have the robot X walking robot, and then of course you have the autonomous wheelchair. So there are many applications that you can think of for that can actually be done with the robots. And then of course something that's actually close to my research will be the robot-assisted surgery. So robot-assisted surgery meaning that you are using the robot to assist the surgeon in doing the surgery. So this is not entirely autonomous. So meaning that it's working with the surgeon, with the surgical team in doing the surgery. So there is this auto dock. So it typically consists of the manipulator of the end of one end that's actually operate on the patients, and then a console where you actually do the planning of the surgery and so on. So this is for bone surgery, and then this is another. So if you actually look at this is a master and slave robot, and then this is another master and slave robot. The Da Vinci is actually a very popular one. So you have the robot. This is the robot manipulator, robot arm, the slave end that's actually operating on the patients. And then you have the surgeon that's actually away from the patient bed. So this is a patient bed. And then what the surgeon here is actually he will look through, and then there's actually a camera insert into the patients, and then these are the two tools that actually operate onto the patients. So this is called a master and slave robot. So what you see here is we can actually see that there's a shift from industrial need to the medical robots. So in 1979, you have a definition saying that a robot is a reprogrammable, multifunctional manipulator designed to move material, transportation of material, parts, tools, or specialized device through various program motions for the performance of a variety of tasks. So this was a definition by the Robot Institute of America in 1979. So this is very much driven that you actually need a machine to assist on and/or replace worker that actually created this industrial robot. And then what happened here is with the industrial robot will then actually lead on to the industrial automations. But the industrial robot is also becoming a service robot. It's also evolving to become a service robot. So you have the service robot, and then come the medical robot. And the medical robot will actually then move on for clinical applications. So you can see the evolutions from a robot, from the industrial need to the medical robot. So what this module is about is this module will actually focus on the mechanics and control of the mechanical manipulator. So as I mentioned earlier, will be all about the classical robotics. So classical robotics is the study of the industrial robot manipulator. So this is the industrial robot manipulator. So which actually involve an integrated approach of kinematics. So when we talk about kinematics, it's essentially a study of the geometry of motion. The statics is a study of the manipulator at equilibrium. The dynamics, which is the study of the course of motion. The trajectory planning, which is generating the path the robots must stray. And then the control strategy, that's called about the execution of the path. Then finally, the physical hardware, which is all about building the robot. So this class is all about classical robotics. It's all about robotic manipulator. So if you are looking for autonomous robot, so this probably may not be the course for you. Okay. So if you look at it, the kinematics, statics, dynamics is still a lot toward mechanics. So the mechanical engineering student may have an advantage, but I've come across cases where the electrical engineering student is the top scholar for this module. So you need to know. So there's a lot of mechanics. There's a lot of applied mechanics, but we'll go through them. Okay. So it goes. We'll go through from the basic. So I'll still go through you on how the description of a frame, the right-hand rule, right-hand coordinate systems, but it will be gone through in a very fast manner. At the end of the day, this is still a graduate class. Okay. So when we talk about mechanics, we're talking about the kinematics and dynamics. So kinematics is the study of position and derivative of point position without regard to force which cause the motion. So if I say this pencil move from here to here, and I'm only representing the positions, so this is essentially a kinematics. So what matter in kinematics is essentially the position and derivative of the positions. So dynamic will involve more. So when we talk about dynamic, we are concerned with the motion of the body under the action of force. So there's a lot of definition over here. So this is a quick course for a quick revision for you if you have previously taken the applied mechanics class. So when we say that the dynamic concerned with the motion of the body under the action of force, we are in another word, we are actually talking about the relationship between the force, the action of the force, acting on a robot mechanism and the acceleration they produce. So when we're talking about dynamic, we are looking at the inertia and acceleration. So if the robot manipulator is a rigid body system, the robot dynamic is an application of the rigid body dynamics to the body. So there's another term here, rigid body systems. So what is your rigid body systems? So when we talk about a rigid body system, a rigid body is essentially a collection of particles, and the distance between the particles remains unchanged during the course of motion of the body. So meaning that the rigid body will not be deformed or change shape. So this is the typical robot the robot manipulator that you can see. They make of metal, and then they are very strong. So this is the dynamic that we are actually looking at. And then if we go on to talk a bit more about kinematics, so it say that the kinematic will be the study of motion without regard to force or torque that actually causing it. So this is a robot manipulator. It's a drawing of the robot manipulator. This is a picture of a robot manipulator, a photo of a robot manipulator. And then if we are to represent the robot manipulator itself, a lot of time we'll draw the robot manipulator in this manner. So you have a base. So same thing, if you look at this picture, there's actually a base. And then you have a link, and then you have the joints. So this circle are the joints, and then at the end of this, you have the end effector. So this end effector will actually tend to hold on to a particular object. So this particular object could actually be the tools. So the manipulator with the end effector will actually be holding on to a tool and use a tool in its operations. So you need to know the joint, and you need to know the link. So this is a joint, this is the link, and this is the base. And then at every base, we tend to give, you assign a coordinate systems. And then at the end of the end effector itself, at this point, you also have a coordinate systems. So this is a coordinate system, this is another coordinate systems. So when we actually talk about kinematics, we do not consider the force or the torque that actually causing it, but we're actually looking at all these joint and link and coordinate system, the position and orientations. So we are interested in the position, velocity, acceleration of each joint and as well as each link. So this is the joint. Theta 3, theta 2, theta 1 is actually referred to the rotation angle of the joint. And then the link, so this is the link that's actually between the joint. So what happened here is you have the forward and inverse kinematics. So the forward kinematics will actually represent the joint space. So you turn the joint, you rotate the joint, and then you actually cause the change of position of the end effector. So the change of position of the end effector is at the Cartesian space. So this is forward kinematics. So meaning that you change the joint, change the joint angle, and then the link being rigidly attached will actually cause a change of the end effector position. So this is the forward kinematics. And then you have the inverse kinematics. So the inverse kinematics is the other way. So the inverse kinematic meaning that you specify the endpoint. You specify this endpoint. So meaning that, for example, you say that these points, you give the x, y, you give the coordinate of this point. And then you have to calculate the joint angle so that the manipulator will be able to achieve this endpoint. So this will be the inverse kinematics. So the forward and inverse kinematics is defined as a relationship between the joint position and orientation of the end effector. So this is the joint position, and this is the position and orientation of an end effector. So the position, so for example, if I'm actually looking at this pencil, so I can say that the position will actually tell the specific x, y, z of this pencil. The orientation will actually tell me whether this pencil is actually tilted in this angle, is tilted this way, or tilted this way. So you have position and orientations. So you specify any object, you need this position and orientations. So the inverse kinematic is a lot harder. So when you turn the joint angle and and being rigidly attached, you will then you multiply a series of metrics, and then you will actually get these end effector positions. But when you're actually given a position and then you actually try to calculate backward, you may find that it's not so straightforward. In some cases, you may have no solutions. You can't reach that point. And then in some cases, you have multiple solutions. And multiple solutions may not be necessarily be a good thing. So for example, if I'm going to hold this pencil, am I going to hold this pencil? I can have at this position, I can hold this pencil in this position, in this way. I can also have my hand hold this pencil in this way, and so on. So there are multiple positions to actually hold this pencil. So actually, how do you actually determine the single position for the robot to do it? So there should be there should not be ambiguities. How to rotate? And then so in order to enable this forward and inverse kinematic, you need to know how to locate the objects. So the links of the manipulator. So this is a link, this is another link, this is a joint. The parts that through in a three-dimensional space. So I mean, as a user, as a human, you may actually say that, oh, okay, my water bottle is here, my file is here, my pencil, my mechanical pencil is here. For a robot, you actually have to tell them. So you need a formal method of telling them. So what happened here is you will actually require to establish something called a frame. So a frame is essentially a coordinate system rigidly attached to each object. So this is the object that you are going to manipulate. So this is a cylinder. You have to attach a coordinate system. So this is a coordinate system that is attached to this object. So this is known as a frame. So this is one frame. This is another frame. And then for the robot itself, you always have a base frame, and then the end effector again have a frame. So not only for the robot manipulator that you need a frame for the end effector point, as well as the base of the manipulator, you also need a frame for the object that you're about to manipulate. So you need to have a frame, and then you also need to describe the position and orientation of one frame with respect to another frame. So you have this coordinate system, this coordinate system, this coordinate system, and this coordinate system. So the next question here is how they have to be related. So you have to relate this end effector coordinate system with the base of the robot manipulator. Again, you also need to relate the coordinate system of this cube with the base frame, and then same thing, the cylinder with the base frame. So the base frame. So a lot of time you may actually define the base frame, the global frame, using as the one that's actually on the base of your manipulator. But this may not be the case. You can actually have one that's actually outside of at a particular point in the room. So you need to describe the positions and orientation of one frame with respect to another frame. You also need to know something called differentiate or instantaneous kinematics. So when we talk about the instantaneous kinematics, the word instantaneous will actually tell you actually imply that this is at a specific point of time. So the instantaneous kinematic analysis of a manipulator will deal with the direction and magnitude of the impending motion at a specific point in time. So what happened here is we are going to be interested only at that particular point in time when we actually talk about this differential or instantaneous kinematics. So when we actually talk about this differential or instantaneous kinematics, we need to know the Jacobian of the manipulator. So the Jacobian is essentially a metric. In robotics, Jacobian is essentially a matrix which provides the relationship between the joint velocity and any effector velocity of a robot manipulator. So in all my lectures, from time to time, I may have supplementary notes. So most of the time, these supplementary notes will be handwritten. So what happened here is I may come across, there are students that ask me questions along the way, and then so last time, in a classroom setting, we'll have it written it on the whiteboard. So in the LT system itself, we tend to write it down on the paper and then just present it. So if you actually talk about Jacobian, the word Jacobian is actually not, Jacobian metric is actually not strictly from robotics. It's actually originated in mathematics. So in mathematics, it is essentially a multi-dimensional form of derivative. So for example, you have your y1 equal to f1, x is a function of f1 of x1, x2, x3 to x6. y2 is a function of f2. And then y6 is a function of f6. You can actually represent it as a vector notation. Y is equal to fx. So what happened here is when we use a capital Y and capital F to actually represent the metric form. So if we actually differentiate them, the yi as a function of a differential of xj, you will have your partial differential delta y1 equal to delta f1 divided by delta x2, delta x1 plus so on. So you do the same for delta y2, you have this set of equations. So again, you can actually represent it as a vector notation. You have your delta y equal to delta f, delta x, delta x. So what happened here is this f over x is a 6x6 metric of partial differential. So this is your Jacobian matrix in mathematics form. So if you actually, so instead of writing it in this form, you can actually put as a capital Jx. So if you divide both sides of the differential time element, you have your y dot equal to Jx x dot. So this is the time varying linear transformation that map the velocity in x to those in y. So in robotics, so this will actually relate the joint velocity to the Cartesian velocity. So if you go back to the slides, it will be something like this. So the definition of a Jacobian will be, it's a matrix that provides the relationship between the joint velocity and n effector velocity of your robot manipulator. So this is the joint velocity theta 2 dot, and then this is the n effector. So the Jacobian metric will actually provide this relationship. So it's a mapping between the velocity in joint space to velocity in the Cartesian space. So the n effector is at the Cartesian space. And then the velocity theta 2 dot and theta 1 dot here is actually the velocity in the joint space. Cartesian space, you have your y dot, x dot. So this is the Jacobian matrix. So there may be a situation where you have come across something called singularity. So when you have singularity, meaning that the mapping is not inversible. So in this module itself, we actually talk about a lot. We'll talk about the singularity and so on. Okay, so So what happened here is the Jacobian will also be used to map the static force. So we mentioned statics just now, equilibrium situation, positions. The static force meaning that you actually have a point where you actually have a equilibrium. So at the equilibrium, the static force will be the force acting on an object that does not change the size, positions, or direction of that particular object. So this is the static force. So the Jacobian will actually be able to map the static force in the Cartesian space to the joint torch in the joint space. So the τ1, τ2 is a joint torch in the joint space. And then the static force is in the Cartesian base will be your Fy and Fx. So when you actually look at the inverse of this, you have this J transpose. You have the J transpose is different from the J inverse. Okay. Any question? So what happened here is will be, so the entire module is going to be all about this. Okay. Yes. So in some cases, you may actually want, preferably you may actually want to use a Jacobian inverse of inverse of Jacobian, rather than Jacobian transpose. So it's actually depends on the situation. We'll go through them in the lecture. So like for example, if you have when you're actually dealing with the joint torch, it's better to use a J transpose. Yeah, we'll be going to that. Okay, then that's the kinematics, and then now we have the dynamics. So when we talk about the dynamics, we are looking at the manipulator equations of motion. So the manipulator equation of motion will actually describe the force required to cause the motion. So you have the joint force as well as a joint torch. So if you have the joint torch, it's better to use the J transpose. If you have a joint force, it may be better for you to use a joint inverse, the J inverse. We'll talk about it when we actually come to the class, come to this topic. Okay, so the dynamic will be about the manipulator equation of motion. So the manipulator equation of motion will actually describe the force required to cause the motions. So you have the joint force and a torch. So this is the joint force and the joint torch on the manipulator, and then this is the end effector. So it will actually cause the joint motion, and then the motion, when you actually talk about the joint motion, you actually cause a motion of every link. So this is the link. The equation over here is a general manipulator equation of motion. So where you have the M, we're actually representing the mass, the Q over here representing the joint, Q dot, and then you have the centrifugal force, gravity over here, and finally you have the joint torch. So this is known as a general manipulator equation of motion. So when we talk about the dynamics, we'll talk about that. You need to know you need to know physics. So for example, you actually need to know like things like F is equal to ma. So, but when you actually talk about F is equal to ma, you are essentially looking at one single particles. You have one single block. But what happened here is when you have a rigid body itself, the direction of the acceleration and force may not be a line. So this will be the topic in the second half. Then we come to the robot system component. So the robot system component will actually from this overview diagram itself. This is the robot manipulator that we have been keep talking. So So we are getting close to the design of the robot, which is the hub, the physical part of the robot systems. So for the robot manipulator itself, you have the actuator, the dryer, amplifier to actually drive the robot manipulator. And then you have sensors that actually provide the internal sensory feedback. So you provide the sensory feedback on the position, velocity. And then the controller can be a computer, so a robot controller, which is typically a controller, a computer. And then there's also a specific task planner that actually fit into the robot controller. So the task planner will actually input the desired robotic task onto the task planner. So task planning itself can actually be broken down into motion command, force torque command, as well as a strategy to react to the force and torque. So this is the robot manipulator. So when you know how the manipulator is actually interacting with the rest of the component, then the next thing is how can we actually design the robot? How can we actually design the manipulator, this robot manipulator? So to design this robot manipulator, we say that the robot manipulator will actually be comprised of the joint as well as the link. So you have the joint as well as the link. So the type of joints is the first thing that you have to consider when you design a robot. And then you also need to consider the actuator as well as the power transmission. The actuator meaning motors, the power transmissions. And then the degree of freedom, whether is it going to be a specialized or is it going to be a universal robot. So and then you texturality consideration. So you have to the texturality over here refers to how good you can the manipulator be used to accomplish a task. So in that case, you have to consider the geometry as well as the workspace. Then you have to consider the speed, size, load capacity of the robot. And then you also need to think about how rigid is a robot or how flexible is a robot going to be like. So the type of sensors that you're going to use. So these are all aspects that you actually need to consider when you're going to design a robot manipulator. Do you want a break? We have a 10 minutes break, and then we'll resume the class at 7 o'clock. One word about the project. So the project, please do not look for your own team own friends to form a team. I'll randomly assign you group member. Yeah, I'll randomly assign you group member. So it's good to know friends. Yeah, it's good to know new people. Yeah, please don't form your own group. Yeah. If I'm too soft, yeah, please let me know. So I'm actually using the clock at the back as a reference. So now I actually look at the clock there and my watch. So there's a bit of about 1 minute of, about 1 minute different. Oh, okay, the in front one is. So they are all not synchronized. Yeah, thanks for pointing out that. So this is 59, and then over there is 7 o'clock. Yeah, okay. Okay, now I see. Yeah. Okay, I think the record. I don't know which the recording is based on which one. Okay. Yeah. Can I have your attention? We'll resume the class. Okay. So what happened here is we're going to talk about the designs of a robot manipulator. So the purpose of this introduction of robotics is so that everybody will be on the same page. So you actually come across a lot of definitions. So these definitions are actually kind of useful because we'll be referring to them as we in the remaining lectures. So when we actually talk about specifying a robotic task, we are actually looking at the task itself could be comprising of a positioning as well as the orientations. So positioning, you place your pencil at a specific point, and then orientation, you may actually place the pencil in a specific orientations. So an object will always be specified by its position as well as its orientation. And then the robotic task that typical to a classical robotic will be the force movement that actually exert on the environment. So when you actually place a pencil on the table over here, so what happens is there's actually a force that's actually exert on the table. So when we actually talk about the robotic task, we're actually dealing with these two things. So a typical robotic manipulator can be considered as something called an open kinematic chain serially connected. So when we talk about open chain, the open chain meaning that the movement of one joint is independent of the other joint in the chain. So this is the definition of an open chain. So if you actually see an open chain, then of course you will ask what is considered a closed chain. So a closed chain meaning that the movement of one joint will cause the movement of the other joint. So they are not independent. So what about kinematic change? So a kinematic change is defined as an assembly of rigid body connected by joints to provide the desired motion that is constrained. So this is the definition of a kinematic chain. So it's deal with an assembly of rigid bodies. So the serially connected, meaning that you actually one at a time. So serial meaning one at a time, parallel, you will have multiple at one go. So this is the base of the robot manipulator. You have the joint, and then you have the link. So you have the joint, which is the power-giving connecting mechanisms. So there are different. You'll come across various ways of actually describing drawing a robot manipulator. You will come across drawing something like this. You may actually come across a drawing of a manipulator in this manner. So you have an oval shape instead of a rectangle, a rectangle bar representing the link. And then at the end, you always have an end effector that actually performing the robotic task. So this is the definition of an open kinematic chain and serially connected. So we look at the joint. So for robotic joints, there are essentially two parts, two types. So there's this rotational joint, and then there's also a translational joint. So these are kind of the characteristics of a general characteristic of a rotational joint, and this is the general characteristic of a translational joint. So for accuracy, the rotational joint will be non-uniform. The translation will be a more consistent one. For rotational joint, the kinematic control will be more complex, coupler, and then it will be kind of difficult. And then a translation joint will be simple coupler, and then it will be relatively easy. So the link design for rotational will be simple, and then translation can be complex. So the dexterity will be, for rotational will be good, the translational will be bad. So this is a general comparison. So it's a typical consideration when you have a rotational or translational joint. So as the number of rotational joints increase, so if you increase the number of joints, so for example, for this manipulator itself, you have more joint now, you put in more joint. So when you put in more joint, your task planning complexity actually increase because you have more joint to actually to accomplish a single task. You actually have more way to do it. And then but your dexterity will actually be increased because you have more joint. So there are more ways to do it. It's likely that you can actually accomplish the task easier. And then the control algorithm will be more complex. But the accuracy will actually be down. Because when you actually have a harder control algorithm, your accuracy will tend to decrease. So this is kind of a guideline. So when we continue with the robot joints, so the both basic type, we talk about the rotational as well as the translational. The rotational is also known as the revolute or rotary joint. So this is a link, this is another link, you have a joint axis, that connect them. So this is a rotational joint. So you may come across, instead of calling it a rotational joint, I may call it a revolute joint. So they are all referred to the same thing. And then a translational joint will typically be represented in this manner. You have link 1 and link 2. The direction of motion will only be in these directions. So if you look at these rotational joints and so on, you can actually see that they are essentially one dimension. Yes? Accuracy is non-uniform. Oh, you don't understand why the rotational... okay, so you have your... So the accuracy for the rotational, you have 1 degree, 2 degree, 3 degree. So your 1 degree, 2 degree, 3 degree will be connected to a link. So your length of the link will actually have an effect. Yeah, so a rotational joint tend to have a non-uniform accuracy. Yeah, yes, yeah. So this is all typically referred to, it's all connected to this thing. Got it? Okay. Okay, so continue with the joint. So to realize a joint, you need an actuator. So the most common actuator for joint is a DC motor. You also need a mechanical transmission system, the physical structures, and then as well as a sensor. So the sensor here will actually, you tend to use an encoder to actually provide the feedback of the motor. So these sensors so for example, in this case, you typically have an encoder to provide as a sensor for the joint. So a physical structure will typically consist of 2 rigid pieces constrained to rotate or linearly move with respect to each other. Of course, you need a bearing. So a bearing will actually to reduce the movement friction. So this is one implementation of a joint. So it can actually be quite complex. So when I actually talk about the actuator technology, you have to, I mentioned earlier that the most common actuator for robot will be a DC, will be a electric motor, and there are many different types of electric motor. So you have stepper motor, DC motor, and then your DC motor may actually tie with an encoder at the back. You have a servo mechanism. So the most common one being the electrical motor, and the most common one is actually the DC motor. So it's the choice of today. The electrical motor is clean, and then on the other end you have the pneumatic and hydraulics. So the pneumatic one is more energy efficient, but it's actually harder for the feedback control. The hydraulic one can actually deliver a large force, but it tends to be bulky, and there may actually be a leakage problem and so on. So, but all these are general. So you've actually come across why, when people ask you why electrical motor is actually being used, it's typically because of this general perception of the different motor. Depending on your application, you may actually choose to use a hydraulic motor. So like for example, but in the case, this is the drive. And then what happened to the end effector? And then you may actually see that for the end effector, most of the time you may actually end up with using a pneumatic one. So you may actually have a pneumatic actuator for the joint. So the mechanical transmission will take the actuator motion and direct it to the joint. So it allows the mechanical transmission will actually allow the change of the rotation direction, change of axis, torque multiplications or reductions. So this is important. The speed reduction to convert the rotary motion to linear motion. So a lot of time, your motor is a DC. When you actually talk about DC motor, the DC motor tend to be a rotational device, and then you have to translate to a linear motions. So you will require a mechanical transmission systems. So you also need to make sure you provide a match between the actuator and load, so that the maximum energy is actually transferred to the load. So there's something called an ideal gear. So ideal gear meaning that the gears are perfectly round, rotate on their true center, and then frictionless. So there's actually no loss. And then there's also a rigid shaft that's actually attached to the gear. So this is a construct of a joint. So and then when you actually talk about the joint, a related question and then the joint link up together in a serial mechanism in this manner. Then the next question is you have this degree of freedom. So when I say this two basic type, a rotational joint or revolute joint, translation joint, each of them only have 1 degree of freedom. So rotation joint only can rotate on one single plane. Translation joint will only be moving in one single plane. So moving on one single plane. So this is 1 dimension. So this is 1 degree of freedom. So a degree of freedom is something that you will come across a lot in the class. So you can actually see the degree of freedom as the minimum number of coordinates required to specify configurations. So for a single particle in plane, the two coordinate will define its location. So you actually have 2 degrees of freedoms. A single particle in space will require 3 coordinates, so it has 3 degrees of freedom. The 2 particles in space have a combined 6 degrees of freedom. So if the 2 particles in space are constrained to maintain a constant distance from each other, so now you actually have the term constraint coming in. So when you have the constraint coming in, then the 6 coordinates must specify a single constraint equation defined by the distance formula. So they must always be maintained in a single distance. So this is, bear in mind that we actually say that this is a rigid body, so it's not deformed. So the distance will always be there. So if the 5 coordinates are specified, the distance formula can be used to solve the remaining coordinates. So in this case, you have the degree of freedom, the DOF of the system will be 5. So you take 6 minus 1, so you actually get 5. So this is one way of looking at degree of freedom. So when I have a rigid body in 3D space, I will have 6 degrees of freedom. So the first degree of freedom, you have the position as well as the orientations. And then with that, you have this low pitch yaw. So the definition of low pitch yaw is actually is borrowed from the aerospace industry. So imagine you have an aircraft that's flying in these directions. So the roll will be along this axis, and then the pitch will be the head of the nose of the aircraft moving up and down, and then this is the yaw, will be along the jet axis. So 3 for position. The rigid body in 3 space have 6 degrees of freedom because 3 for position and 3 for the orientation. So meaning that for this band itself, you have X, Y, Z to actually indicate the center of the band. That's the position. And then you have another coordinates, 3 X, Y, Z, to actually represent the orientation. So the orientation will be a normal to the plane of the object. So typically be normal to the plane of the object. So in robotics or mechanics, the degree of freedom will actually be equal to the number of independent position variables that will have to be specified to locate all parts of the rigid body mechanism. So you have the DOF that you actually learn in applied mechanics, and then now you have the DOF in robotics, which actually refer to the independent position variable that will have to be specified. So, for example, in this case, you have a planar 4-bar linkage. But what happened here is this planar 4-bar linkage only have 1 single degree of freedom. You have 3 moving members, but at the end of the day, you only have 1 single DOF. So we can make the thing easier and say that the DOF is equal to the number of independently driven joints. So by counting the number of joints of a serial manipulator, you will actually tell your degree of freedom. So as your degree of freedom increases, your positioning accuracy will actually decrease. Again, this is a general guideline. So you have more joint, so your position accuracy will actually be decreasing. It's harder to control. There's actually more accuracy issue. And then your computational complexity, of course, increase when you have more degree of freedom. The cost will be increased, but again, you will have more flexibility. So if you look at this, the degree of freedom is essentially equal to the number of joints. So as your number of joints increase, your position accuracy will decrease, your computational complexity will increase. The cost, of course, it will be increased because you have more joints. You can do more things. Your flexibility will increase. And then, of course, the power transmission will be more difficult. So you need to make sure you can actually transmit the power to all the joints, all the independent joints. Then you can also, so for a different manipulator itself, you can also classify them according to the coordinate system. So you have the Cartesian coordinate system manipulator. So Cartesian coordinate system manipulator, essentially, you have your x, y, z. So what happened here is you have 3 linear coordinators. This is your x, this is your y, this is your z. And then the n effector, over here you could actually have a width. So this is your n effector. You can actually do a roll, pitch, and yaw. So this is a Cartesian manipulator, a Cartesian coordinate system manipulator. You can also have a cylindrical coordinate system. So what happens in a cylindrical coordinate system is you have z, r, and theta. So z, so this manipulator itself is moved along this single z. And then you have your r, which is the radius of the cylinder, and then the theta will actually be the angle that actually make with the horizon. So this is cylindrical. So you have 2 linear and 1 angular coordinates. You can also have a spherical coordinate system. So a spherical coordinate system itself will have the r, which is the radius, and then you have 2 angles for the spherical coordinate systems. And then with that you can actually we look at a workspace. So the workspace is actually defined as a locus of position and orientation achievable by the n effector of a manipulator. So I mentioned that this is an n effector. So this is an n effector. So where the reach of the n effector will actually define your workspace. So for example, if we take example of this cylindrical robot, and then this shaded area itself will actually define the workspace. So you can't have this manipulator that come to here, but you cannot go beyond this part. So this is corresponding to this void area. So this is the workspace that you are actually working on. And then similarly for spherical mechanism robot in this manner, this is the workspace. So when you actually talk about the workspace, you have something called a textureless workspace, and then a reachable workspace. So a textureless workspace is defined as the locus of 2 positions in which all the 2 can be oriented in all possible ways. So meaning that if for this single object itself, at this particular point, if my hand is a robot, I can hold on to this. I can reach this point in all different ways. So this will be a textureless position, textureless workspace. So a reachable workspace, meaning that I can reach regardless of its orientations. So even if I only have one way of reaching that point, so this is considered a reachable workspace. So with that, we can say that the textureless workspace is usually much smaller than the reachable workspace. So because for a reachable workspace, you don't have the requirement that you can for that particular point, you have to reach in all orientation of your manipulator, in all configuration of your manipulator. you can reach. If you can just reach the point, you will be fine. You will be all right. So this is the definition between the textureless workspace and reachable workspace. We also have to, so when you're actually designing the robot, you also have to consider the operating environment. So for example, if the robot is actually to use in a clean room environment, you have to evaluate internally with suction in order to take away all the particles generated by the friction surface. And then you may actually have to employ magnetic washer to hold the fuel magnetic lubricant in place as well. So there's also situation where your robot is going to work on a manipulator is going to work on a harsh environment. So for example, spray painting. So you have to coat to minimize the contamination of the joint by the airborne paint particle. So for example, you may have all this. So after you have designed the robot, of course you need to you have to specify the performance of the robot. So you specify the performance of the robot, you're actually looking at you look at the first thing that you're actually looking at is called the resolution. So what is the resolution of your robot? And when you talk about resolution, you have something called a control resolution. So a control resolution refers to the smallest incremental change in tool position that the control system can distinguish. So you assume no dead band, sensor error, computational problem, and all those things. So basically, it only depend on the type of joint, resolution of joint position, sensor, and number of joint. So for example, if I have these single illustrations, so the robot can point at this point and then move to another point, third point, and so on. These are all equally spaced points. So between these 2 points, this is known as the control resolution. So this is the smallest incremental change in tool position. The tool position that's actually held on by your end effector. So the control resolution can be computed by dividing the total distance traveled by the total number of discrete points that the mechanism can resolve. So this is a total point that can be resolved. This is the total distance. So you divide them, you have the control resolution. So the control resolution essentially talk about the distance between the two adjacent points. If you look at it on a single plane. So, but what happened? We have to consider the effect of mechanical inaccuracy, and then sensor error. So what happened here is you end up don't have a specific point, but you have a zone. So so in all mechanical systems, so you can't really even with your hand you can't always point your pen on a single spot. So the same thing for the robot itself. You will be a zone. You have because of the inaccuracy. So this is known as, so you have something called a spatial resolution. So the spatial resolution will be the worst case system between two adjacent positions. So you have to consider the variation due to the mechanical inaccuracy over here. So this defines the zone. So this is your control resolution, and then you know that the point may not fall exactly on the point, but instead it will actually off here. So this is defined as a zone. And then if you have this end to this end, you have the spatial resolution. So this is the control resolution, and this is the spatial resolution. So for every robot itself, you will have to look, robot manipulator itself, you have to know their resolutions. The resolution itself will actually define the quality of your robot manipulator. So when we actually talk about the accuracy actually refers to the ability to place a tool tip at an arbitrarily prescribed position in the workspace. So again, we look at this one-dimensional illustration. So if this is the target position, and then this is your planned closest position. So it will actually define your accuracy. So your accuracy, how do you actually measure the accuracy? So your accuracy will be equal to the worst case distance from the target position. So the worst case distance from the target position will actually be equal to half times the spatial resolution. So you have the spatial resolution from here. So this is a spatial resolution. And then from this spatial resolution, half times the spatial resolution, so this is the target position, will actually give you the accuracy. So when you actually look at robot manipulator itself, you need to know all this performance, all this. When you actually want to specify your robot for your specific application, you need to know all these things. So accuracy is essentially the measure of the ability to place a tooltip at an arbitrarily prescribed location in the workspace. There are two accuracy. There's something called global accuracy, and there's actually something called a local accuracy. So global accuracy, you will actually consider the entire workspace. The local accuracy you will only be considering the neighboring specified point. Okay. Yeah, it's quite straightforward actually. So you have accuracy, you have resolution, you have accuracy. So accuracy go to half times the spatial resolution. Then you have something called repeatability. So repeatability is also sometimes known as the precision. You may come across people that actually refer precision as a measure of the repeatability. So what happened here is the repeatability will actually be defined as the ability of a manipulator to reposition its tooltip at the position to which it was previously commanded. So that means if I point at this single point, and then pull back my arm, and then point at this again, third time. So how many times can I point at it as an exact position? So for example, in this case, this is the point that you're actually supposed to put. And then your initial position, and then this is your second try, and so on. So when you actually want to measure the repeatability, you can try to blanket the hits, how many hits within the blanket, and measure the distance across the zone. So this will actually define your repeatability. And then, so you have position, you have resolution, accuracy, and then repeatability, and the next thing is the speed. So you want to do it accurate, precise, and then you actually want to do it fast. So when you actually want to do it fast, you can actually measure the tooltip speed. The standard will be something called a standard cycle time. So a standard cycle time will actually measure the time to take the robot arm, the manipulator, to travel up 1 inch. So when you travel up 1 inch will be actually about 25 mm. Go across 1 foot will be about 300 mm, and come down 25 mm. And then after that, you come back through the same path. So you go there and then come back. So this is known as one cycle time if you go there and come back. So if you actually look at the cycle time, so in 1985, which is the first production direct drive robot, you can actually achieve a cycle time. The cycle time will actually very much depend on the load. So of course, if you carry a lighter load, you will tend to be able to do it faster. If you carry a heavier load, you will not be able to do it as fast. So for 20 pounds, you can actually have a cycle time of 1.7 seconds. So last time this was a big deal in 1985. So this is considered very fast. But in today, the robot can actually do very fast, a lot more, 10 times faster. So you're looking at the design of the robot. So when you do the design of the robot, you need to consider all this. And then after that, you need to think. After that, we'll be actually looking. After that, you need to think about the trajectory. So, what about trajectory generations? So you have a robot manipulator. So this is point A. This is point B. So you want to move from point A to point B. You need to determine the path. So you need to determine the path. So you have to move the joint smoothly so that you can ensure that the A to B will actually follow this smooth path. So to do that, you will actually require you to do interpolations. So we define trajectory as a time-based function. We specify the position and higher derivative of the robot mechanism for any value of time. So not only the position, you also have to consider the velocity as well as the acceleration, so that you can actually have a smooth path from A to B. And then to have a smooth path from A to B, you need to have a coordinated motion of joint to provide the desired end effect motion, the end effector motion. So we'll be going through this trajectory generation as well. Okay. So recap on degree of freedom as well as the resolution. So when we actually look at robot manipulator, so this is one way of depicting a robot manipulator. You have the base, you have the joint, and then you have the moving lane that's actually go between them. So in this case, you have M moving lane, and then you have M one degree of freedom joint. So I mentioned that all the joint is either rotational or translation. So a rotational joint is 1 degree of freedom, a translation joint is 1 degree of freedom. So a ring is a rigid body, so there's a 6 parameter altogether, 3 for position and 3 for orientation. So 1 degree of freedom joint will have 5 constraints. So when you have M moving lane, you will have 6 M parameters, and M1 degree of freedom joint, you will have 5 N constraints. So the degree of freedom of the system will be 6M minus 5M, which is actually equal to M. Okay. So degree of freedom is important. So you need to know them well. So for industrial robot, every mechanical part of a robot, except in the gripper or tools, there will be some form of joints that actually induce the motion in the robot part. So this is called a degree of freedom. So when you look at the robot manipulator itself, you can actually tell the degree of freedom of the robot manipulator pretty easily. You can simply count the joint. But you need to know why you can simply count the joint. So a human arm will have a 7 degree of freedom. So a human arm will have a 7 degree of freedom. So you have this. This is a shoulder. This is a shoulder. So a shoulder will have a roll, pitch, and yaw. And then the elbow itself, you will have the pitch and yaw. And then the wrist itself, again, you have the wrist pitch and wrist yaw. So you see this is a drawing on your shoulder, and then you may actually depict the drawing of the joint in this manner. So you have a single frame attached here, and then you have the base frame over here. So you have 3 that actually join together, but you can actually expose them, and then from here you can actually see that they actually consist of 3 1 degree of freedom joint. Okay. So this is this. This is this, and this is this. So we mentioned earlier that the roll pitch yaw that actually come from the airplane industry. So this is roll, side to side is yaw, pitch will be up and down of the nose. So our human arm has 7 degrees of freedom. And then when you actually look at a general robotic manipulator will have 6 degrees of freedom. And then our end effector, which is our human hand effector, which is our human hand, have a lot more degree of freedom. So this is from one of the, so this is the joint of the human finger. So every one itself have a degree of freedom. And then you can actually have up to, you have more than 20 degrees of freedom for our human hand. So our human hand is actually a lot more flexible. So control of our human hand can actually be a lot more harder. So this is a degree of freedom that you actually need to know. And then the next thing is the resolution, spatial resolution, accuracy, and repeatability. So you need to know this for particular region. So when you want to specify your robot, when you are given a new robot, these are parameters that you may actually need to look at. So after looking at all these parameters, the next thing that you actually need to look at is the kinematic of the manipulator. So what is the resolution? So the resolution or control resolution is the smallest increment that the robot controller can control by means of a D to A or A to D command. So DACS. Digital to analog converter system. For position feedback as well as the control. So for example, if I have a robot arm, so moving around a bar in this manner, so this distance is 40 cm. So this is a D, this is a robot arm, and then you have a gripper over here. So you have a sliding arm, can traverse a distance of 40 cm upon receiving a 10 bits DACS for position feedback and control. So your control resolution, CR, will be D divided by 2 to the power of N. So 40 cm divided by every increment, every increment. So the increment you have 10 bits, so meaning that you have 2 to the power of 10 combinations. So you end up with 40 cm divided by 2 to the power of 10. 2 to the power of 10 is 1024. So your control resolution is 0.03906 cm. Okay. Okay, so this is control resolution. And then what about the spatial resolution? So the spatial resolution will be the smallest increment of motion achieved by a robot manipulator as its true or end effector. So it's a combined resolution including the control resolution and motion inaccuracy. So this motion inaccuracy can actually be derived from originate from the mechanical or dynamic interaction of the robot with the environment. So this is the spatial resolution. Accuracy will always be defined as half of the control or spatial resolution of a robot. If you are given the spatial resolution, half of the spatial resolution will give the accuracy of your robot. And then you have the repeatability. So the repeatability is defined as the ability of the robot to return to its top position. So you teach a robot to always position the pen onto a single point. So you want how often, how good is the robot in actually return to this top position will be your repeatability. So your repeatability will actually be influenced by your control resolution as well as your mechanical inaccuracy. So if we put everything together, you actually end up a diagram over here. So this is your first position, this is your second position, this is your target position. So this is the tooltip. So the accuracy, you define the accuracy at 0.5 mm. So this is from your target position to your tooltip. And then from one position to another adjacent joint position will actually give you the resolution. So this is 1.6 mm. So if you actually consider that this position, this joint position, this control position will be actually be affected by the by mechanical inaccuracy. So you have to consider the inaccuracy in. So what happened, the mechanical instability in, so you will have this zone of 0.4 mm. So you have this zone of 0.4 mm, and this is the target position over here. So this 0.5 mm is actually at the center of this 9. So this is 0.2 mm, 0.2 mm. So 0.2 plus 0.8 mm, you have 1 mm of accuracy. And then if you, so same thing, you have to, if you consider the mechanical instability at one point, you have to consider the mechanical instability at the adjacent point. So you put them together, you will find that you have a 2 mm of spatial resolution. Okay. When we talk about trajectory, we have to coordinate the motion of the joint, and then related to the trajectory, you will have the control of the motion. So control of the motion over here will actually refer to the position control. So you need to have a stable and robust algorithm to coordinate the joint motion and enable the robot to follow a specified trajectory. So it can be point to point, or it can be actually be trajectory following. You can also have independent joint control or inverse dynamic control. So in this case, it's involved the compute of it's involved computed torque. So you also have non-linear control approach, where you have the robust control, adaptive control, and so on. So control will be taught in the second half of this module. Force control. So the force control is referred to the ability of the manipulator to control force or contact. So this is complementary to the position control. So you have position control, and then on top of the position control, you may actually want to have force control. So like for example, a window washing task, you will actually need to have something called a hybrid position force control. You have to make sure that the force that's actually exerted on the surface, a certain force exerted on the surface, so that you can actually wash the face. You can actually cleanse the surface. And at the same time, you have to make sure that you can move the controller. And then you don't want to clean the surface in such a way that you actually break the surface. So you actually require something called a hybrid control, hybrid position force control. There's also a compliant control that's actually allowance for the deviation from its own equilibrium position. So this is usually depending on the applied external force. And then you will also there's also an impedance control that actually uses a force torque measurement. So there are for different motion control method, you have for point to point, you actually refer to the path between the point, not as specifically controlled. So there are different applications for it. So for example, the spot welding, the pick and paste, essentially all point to point, loading and unloading. So you may find that a lot of applications actually involve point-to-point applications. Continuous path. So the end effector must follow a prescribed path in a 3D space. The speed may change or may need to be accurately controlled. So the spray painting, the arc welding, gluing will actually require a certain speed. So you have control, and finally, you need to program the robot. So when you program the robot, there are essentially two ways to program industrial robot. The first thing is actually via something called a read-through programming. And then the second way is actually via something called a textual robotic language. So the read-through programming, meaning that the desired movement are actually stored in the controller memory. So you use a teach pattern. So you will see. So if you for example, if you buy a UR5, UR10 robot, the manufacturer will actually give you a teaching pattern to allow you to control the robot. So you may use a teaching pattern for power read-through programming of the robot. So the Pro is simple for point-to-point movement. So we mentioned earlier that a lot of time we are actually dealing with point-to-point movement. So the teaching pattern will be very good in doing that. But the con itself will actually be very tedious for the complex movement. So spot welding, material handling, and so on, you can actually use a teaching pattern to do it. So there's also something called a manual read tool. So this is also known as the walkthrough. So you hold on to the end effector, and then you move the end effector physically by the programmer. So you can actually use it for continuous path movement. So instead of having a teaching pattern is like a tablet, and then you have a pattern to do it. And then a physical read tool, meaning that you have a robot, you hold on to the end effector and move them. So these are the read tools. So the manual read tool will be difficult if you have a very large robot arm. So you will find yourself very difficult to move the end effector, the end effector of the robot manipulator when you actually have a very large robot arm. But the manual read tool will be very useful for continuous path movement. So this is example. So this is a teaching pattern, and then this is a read tool. This is a manual read tool. So teaching pattern, the operator is using a teaching pattern to program this robot. This is a physical read tool. So when you actually program the robot itself, you have the read tool programming. And then the other way is actually via something called a textual robotic language. So a textual robotic language is actually close to human language, so that it's easier to understand and program. So the first textual robot language actually come out in 1973. So it's known as Wave. And then it's used to interface the machine vision system with the robot. So at that point in time, the robotic community have started, the machine visions have developed to a certain digital electronics, the digital image processing have developed to machine vision systems have developed to a certain stage where they are used together. So this is in 1973. But the first common textual robotic systems was developed in 1979. So this is known as the VAL systems. So in 1984, there's an upgrade. So this is known as the VAL2. So if you look at the VAL language, so for example, if you have the task description in plain English, move to P1, which is essentially a general safe position. This is a command. And then when you have your VAL itself, you will have move P1. Move P2, move P3, and close, and so on. So the closed eyes will actually refer to the closed gripper. So when you actually look at the VAL language and the text and the task description itself, you can actually see that they are actually very close. So it's easy for you to understand. So along the way, there are also other textual robot language. So there's manufacturing control language, the MCL, the real automated programming tools, AMLs, and AutoPass by IBM for assembly operation, etc. So as an end user of the robot, you may actually end up using the textual robot language or the teaching pattern to program a robot. So, of course, when you actually look at all these things, you have move P1, move P2, and move P3. The next section, you may actually ask, how could the desired motion be easily implemented on robots? So to do that, you may actually want to consider robot simulations. So robot simulation is very much an in thing now, the thing that actually people try to do in the research community. So they will have a very high fidelity, very high accuracy, very high, very complex simulations, and then they use robot simulations to do an offline programming, and then after that use it to program the robot. But for industrial robot itself, we'll still see that the textual robot language as well as the teaching patterns are commonly used. So robot simulations is the next thing. And probably it will be there. So look at specific robot systems, a Scala. So this is a popular option. It's an example. Is a popular option for small robotic assembly operations. So what happened here is this stands for Selective Compliant Assembly Robot Arm. So you have this SCARA. So the jack is rigid, so you move around the jack, and then one direction, and then you have the X and Y compliant. So this, if you actually look at this configuration itself, this is the same as your cylindrical manipulator. So you talk about the cylindrical coordinate system. So this is essentially the same as your cylindrical manipulator, cylindrical coordinate systems. So the joints are direct drive motor. So the direct drive motors is like the starting of the direct drive motor is essentially a milestone in industrial robotics. So if you look at the specification itself, you'll come across all these items. So you will talk about the reach, the vertical stroke, the maximum payload, the repeatability, cycle time, and so on. So this is the work envelope. And then they also tell you, and then this is the robot controller that actually associated with it. So this is an old system. So they have old CPU, old microcontroller. So this is a Motorola 68000 CPU, which is actually run at 10 megahertz. So now your computer, you can use your CPU is easily running at 1 gigahertz. So serial port, you have 5 RS-232. The RS-232 is a serial port. So RS-232C is the protocol. Okay. So this is a quick run through of what is a robot and the basic component of a robot. For this course itself, we are dealing with the classical robotics. So it's a study of the industrial robotic manipulator. But what happened here is we'll be focusing a lot more on the kinematics, statics, dynamic, trajectory planning, and control strategy, and the integration of these items. Okay. So we'll not come back to talk about the resolution, the sensor, actuator, and more, etc. But we'll be going on, the next lecture we will be going on to talk about the kinematics. Okay. So if you ask me, after learning this course, can you be a robot? Yeah, you have the theoretical basis for the robot, for a robot manipulator. So this is not a hardware course. It's not an electronic course. Okay. So there are some homework that I need you to do. So on the canvas itself, you'll find a few sheets of notes on the linear algebra. So you need to read through them. And then for your assignment, you will be using MATLAB. So what happened in NUS is that your school fee actually pay for the MATLAB license. So please download the MATLAB, and then you will be using it. So you'll be using the MATLAB. So please, if you haven't done that, please download the MATLAB. So last time I will just let the student go back to read the notes, but I think it will be better if I use a lecture hour to take a quick go through, but it doesn't substitute that you need to go back to read the linear algebra, to revise on your linear algebra. So you have to understand. You must understand what is a metric. So a metric will be an m by m array of number. So m is the number of rows, n is the number of columns. So we always specify a metric with a bold letter A. So in some cases, we may not be so rigorous. So you have to understand in context. But usually, a bold A will represent a matrix. So a scalar quantity will be a small a. Iterate. So your A11 to ANN will be specified as Aij. So I is equal to 1 to n, 1, 2 to n, j is equal to 1, 2 to m. So there are different types of special matrix. So a square matrix meaning that the m is equal to n. You have diagonal, identity, as well as metric matrix. So please refer to the notes to understand what is metric. And then a column vector. So what happened here is for a column vector you have m by 1. So a column vector m by 1 is a special metric. A row vector 1 by n is also considered as a special matrix. So if we define a vector as a metric with only one column, all vectors are inherently column vectors. So meaning that if I have a vector as a metric with only one column, so that means all vectors are inherently a column vectors. So you need to know what is inner product. So inner product, another word for inner product will be dot product or scalar product. So when you do an inner product of two vectors, x and y, you will denote by x dot y, so you will have x1, y1 plus x2, y2 plus xm, yn. So this is your x, this is your y, and then you need to know the norm. The norm or length of vector x in Rm. So this R refers to the real space, n refers to the M space. So N space is the set of all n set of real number. So when you talk about the norm or length of a vector, they mean the same thing. You can actually denote it in this manner, or this manner is actually equal to the square root of x dot x, which is your square root of x1 square plus x2 square plus xm square. You also need to know the cross product of two vectors. So the cross product of two vectors are important. So if you have x cross y, so you have your x, which is the magnitude or length of the vector x, and y is the length of the vector x sine theta m. So theta is the angle between x and y, and is a unit vector at the right angle to both x and y. So this is important because you'll be using something called a right-hand coordinate systems. So a right-hand coordinate systems, when you actually want to attach a frame to the base of your robot manipulator, you see that we draw the coordinate on the cube, on the cylinder. So this frame, the x, y, and z, the coordinate, will have to define according to the right-hand coordinate systems. So the right-hand coordinate system meaning that if I specify my x and y, my z will always be defined in this manner. So you have your right-hand coordinate systems. So for example, if this is a cylinder, sorry, this is a cube, and I define the frame on this cube, the x in this direction, y in this direction, the z will have to point in this direction. So this is the right-hand coordinate system when you actually define all the frame. So the right-hand coordinate system will, so with that, you can actually say that the x cross y will actually give you x cross y, which is actually at this angle. So the x cross y in the right-hand rule is actually closely related to your right-hand coordinate systems. So length of a cross product is the length of the x times the length of the y times the sine of the angle between the x and y. So you need to have this. You need to know this, and then you also need to know the linear independent. So this is a definition of the linear independent. You can go back and read. So the dimension of a linear space is defined as a maximum number of linearly independent vectors in the space. So if I have Rn, you can find at most n linearly independent vector. So this Rn over here is referred to a real coordinate systems of dimension n, which is a coordinate space over the real number. So when I have R squared, I'm actually referred to a single plane. Okay? So a set of linearly independent vector in Rm is called a basis if every vector in Rm can actually be expressed as a unique linear combination of the sets. So this is a revision. And then, of course, we talk about J transpose before the break. So the J transpose, what is a transpose? So if I have an A, which is earlier on, so this is my A. My A transpose will be equal to this. So A11 to A1n, A11 to AN1. So it will be a transpose of the systems. So you have to bear in mind that when I have A plus B transpose, it's equal to A transpose plus B transpose. But when I have A times B transpose, I'm actually equal to B transpose A transpose. So you need to know all this. You need to remember all these things. You will actually come out when we in the subsequent lecture, when we do the deviations. So a metric A is said to be symmetric if A is equal to A transpose. A metric A is said to be skewed symmetric if A is equal to minus A transpose. So for any metric A, B is equal to A transpose A. Is a symmetric metric. So that besides that, you need to know the rank. So the rank of the metric A is the maximum number of linearly independent columns or rows in A. So these are the definitions. So please go back and read. Jacobian is always very important. You need to know Jacobian well. So if I have X belong to a set of Rn, then dxt dt will be equal to dx1t dt and dx, sorry, this is d, this is dt, dxnt dt. So you put it as a metric form, it will be da dt, dai dt. So if Jx is a scalar function of x belonging to Rn, then you will have this delta j over delta x1, delta j over delta xn. So delta square j, delta x square will actually be equal to this. So please look at the notes. And then you need to know the trace of A. So trace of A plus B is equal to trace A plus trace B. Trace of AB will be equal to trace B transpose A transpose. So it's equal to trace BA. So trace AT BT. So if you decided to continue with this course, please study the notes on linear algebra review. Okay? Okay. Okay, so the next thing is MATLAB. I guess for most of you, probably should be quite familiar with MATLAB. But for some of you, may not be familiar with MATLAB. So if you're not familiar with MATLAB, please work with it. And then for those who have previously taken the machine vision class, so you should have already downloaded and be familiar with the MATLAB. So MATLAB, essentially, we can actually use to simulate the robotic system with accurate kinematics and dynamic property. So you don't want to, so you see, just now if you look at the linear algebra, there's so many deviations and so on. So it can be quite complex and then quite tedious, very tedious. So the MATLAB, with all the metric operation and all those things, will actually help you to simplify it. So few people know that, I mean, many people have forgotten that the MATLAB actually stands for Metric Laboratory. When it actually first started that time, it wasn't that expensive. It was free. So it's like freeware, everybody download and can use. So now it's become very expensive. But of course, in NUS, you have a license copy and then you can make use of it. So the whole purpose here is actually to support metric operation. So it's an interpreter. The interpreter is different from a compiler. So a compiler is, an example of compiler will be C. So what happened here is actually allow you to do quick prototyping, and then it can actually allow you to easily return to in C, C++, or Java. So there's the MATLAB is expensive, but there's public domain open source clone that you can actually make use of. So once you download MATLAB and then you start, you open the you execute MATLAB, you double click on MATLAB icon, and then you actually see an interface like that. This is the command window, this is the workspace, this is your command history. And then you can do vector and metric operations. So if I have A equal to 1, 2, 3, semicolon 4, 5, 6, when I return, it's an interpreter, so it straight away execute this, and then it will tell you 1, 2, 3, 4, 5, 6. So this is a metric of 2 by 3. And then you can do extensions of metrics. And then of course you can, a matrix is a matrix is a mathematical concept. Array is a data structure. So essentially, I have A 1 to 3, 4 to 6. You have A 1, 2, 3, 4, 5, 6 is an array. It's also a metric. So a metric is two-dimensional array often used for linear algebra. So there's some simple example of matrix and array operation. If you haven't been using MATLAB for a long time, you may want to work on it. So we want to try it out. So there's a transpose. There's a metric transpose. So a metric transpose in MATLAB will be A prime. So a metric. So you have your A. So you have initially your A. Your metric A is 1, 2, 2, 1. So A transpose will be 1, 2, 2, 1 as well, because this is a symmetric metric. So any problem you can, if you want to edit any problem, you can actually use a help. So good thing about MATLAB is that you have a good online help systems. So there is also a MATLAB website that you can actually get help from. So Help Edit itself will actually tell you how you can actually edit a file. So you can actually look at getting started with MATLAB. If you don't know, if you have not used MATLAB, or you want to do a reflection of do a revision or you hasn't been using MATLAB for a long time. So download and install MATLAB, and then familiarize yourself with the MATLAB programming environment, type demo, and then try to create some files and so on. Yeah. So this is an introductory. It's a first class. It's an introduction. So these are the two homework. If this is a course that you want to take, then please do the revision on the linear algebra and try out MATLAB if you haven't been doing that. Any questions? Okay. So I've received email from students saying that they have bid for this project, and they have, but they are not given this project. So sorry, they bid for this module, but they are not given this module. Okay, so first of all, you have to ask yourself whether is this the module for you, and then you have to talk to then you have to speak to the coordinator. So just before the lecture, I received an email from the coordinator from ECE, and then according to her, they are actually working on they are processing those appeal cases. So the processing of the appeal cases can actually go all the way until 20th of January. I think first of all, you have to decide. I mean, even for those that's actually given this module, I think you have until next week or the week after to decide whether you want to continue, whether you want to drop this module. So go back and think about it. Yeah. Okay. It's the first class, so I'm not going to hold you for too long. Good night.